Hey guys, Mr. Smith here, and in this lesson we're going to do a lot of review actually of some grade 11 ideas, special angles, exact ratios for certain special angles, and just make some connections to radian measure. So let's get started. As I said, quite a lot of review in this one. Um, Special angles and knowing exact ratios for trigonometry is really useful. There's a lot of applications where, like one example is electronic music, where like certain notes and frequencies correspond to specific trig ratios, and for the math to work out, you need to have like the exact values for specific angles. And you guys in your grade 11 course did look at exact ratios for certain special angles. And again, we're just going to kind of review that and then make some connections to radians along the way. So one of the huge big learnings you guys had in your grade 10 course, grade 11 course, was that you can actually think of, instead of just thinking as angles and as like degrees in a triangle, you can actually make a connection between angles in the Cartesian plane, and you can actually think of any angle corresponding to a unique point on what we call the unit circle. So in your grade 11 course, you might have investigated something along these lines. So here's the unit circle. The unit circle has a radius of 1. And in your grade 10 course, you learned about equations of circles. This is the circle with the equation x squared plus y squared is equal to 1. And you guys made some. Actually, I might move where that I have that radius. Because I want to label something else there. All right, radius is equal to 1. All right. And so you guys started saying, okay, I want a way of showing angles in the Cartesian plane. And so you said in your grade 11 course that we're going to define angles to start at the positive x-axis. So if I wanted to describe an angle like so, we make the x-axis you guys called it the initial arm. So our angles always start on the positive x-axis. We call that 0 degrees. And then they go to some point, and we call this the terminal arm. And every angle between 0 and 360 degrees corresponds to a unique point on this unit circle. And you guys made some further connections last year, and we'll summarize this in a moment, but you guys showed that the x value and the y value on the unit circle that corresponds to a specific angle is actually equal to the cosine of that angle, and the y value was the sine of that angle. All things you guys touched on in your grade 11 course. So interesting about this idea is that once the x values and once you go past 90 degrees, like you're outside of right angle triangles, the x and y values on the unit circle can be negative. Either the x value is negative, the y value, or both, which meant that the cosine and sine of an angle could be negative too. And you guys took that a bit further. We'll get there in a second, but let's just to reinforce this idea of angles corresponding to points on a unit circle. Here are some simple points, right? Look at this unit circle I've drawn here. When the angle is 0 degrees, we're at the point 1, 0. When the angle is 90 degrees, 0, 1. 180 degrees, I'm going to even label these degrees. 0 degrees, 90 degrees, 180 degrees, 270 degrees. Those are pretty easy points to pick off. And if you take out your calculator and just verify this right now, the cosine of 0 is 1. The sine of 0 is 0. This further reinforced in your grade 11 course that, these points in the unit circle actually correspond to cosine and sine. The cosine of 90 is 0. The sine of 90 is 1. the point on the unit circle for 90 degrees, 0, 1. Cosine 180 degrees, -1, the sine is 0, the point -1, 0. And finally, the point 270 corresponds to the point on the unit circle, 0, -1. You guys also looked at the tangent ratio, and if I had an angle and we're on the unit circle, so with like a hypotenuse of 1, and this is the x, this is y. So x was the adjacent side, led to giving you cosine. Y was the opposite side, led you guys to getting the tangent. You guys showed that tan theta is opposite y over hypotenuse x, and that this actually worked for not just angles between 0 and 90, but for any angle. And so what's the tan of 0? You can try on your calculator, but if you just use the rule, you take y over x or sine theta over cos theta, you get 0 over 1, which is equal to 0. The tan of 90 is 1 over 0, which is undefined. Again, these are all things you guys investigated in grade 11. For 180, the tan of 180, 0 over -1 is 0, and 270 is undefined as well. Maybe on your note, you just want to toss in as well maybe what the angle is in radians, just to make some connections here. Remember, 90 degrees is pi by 2 radians. 180 degrees corresponds to pi radians, and 270 will be 3 pi over 2. So those are some exact ratios we know, cosine, sine, and tan, for 0, 90, 180, 270. And those exact ratios are pretty easy to figure out because of the unit circle. They correspond to 4 pretty nice points on the unit circle. As I mentioned before, when you get angles beyond 90, the point on the unit circle can either have a negative x value, a negative y value, or both. And so to figure out, well, when is cosine positive, when is sine positive, when is tan positive, you guys developed a rule called the cast rule. So in quadrant 1, where angles kind of start from 0 to 90, that quadrant is labeled A. All the trig ratios are positive. That's why when you guys did SOHCAHTOA with right angle triangles, in a right angle triangle, all the angles are between 0 and 90. So you guys always got sine, cosine, tan as positive, and nothing was, everything was okay. In quadrant 2, for angles between 90 and 180, only the sine ratio is positive. The cosine and tangent are negative. In quadrant 3, where the x and y values are negative, that gives you a positive tangent. Cosine and sine are negative. And in quadrant 4, only the cosine ratio is positive. And so to summarize it up, CAST spells cast. We call it the cast rule. Again, this is something you guys developed in your grade 11 course. In your grade 11 course, you guys also looked at 3 new trigonometric ratios. They're related to the 3 primary trigonometric ratios. You guys learned about the cosecant ratio. And the short form for the cosecant ratio was CSC. And the cosecant of an angle, it's a reciprocal ratio. It's a reciprocal of the sine ratio, 1 over sine theta. The other 2 corresponding ones to cosine and sine is the secant ratio, which is 1 over cosine, and the cotangent ratio, COT theta, which is 1 over tangent. Again, everything we've done so far, we are just reviewing some grade 11 ideas. All right. And the last thing you kind of do in your grade 11 course is you learn that, hey, there's actually certain angles where I don't need a calculator. I actually can know exactly, without any rounding or decimals, what the trig ratio is. And the 2 special triangles that help you give those angles, I'm going to draw right now. The first one is a 45, 45, 90 isosceles triangle. And if you give these side lengths a length of 1, the 2 legs, you can use Pythagorean theorem. 1 squared plus 1 squared is 2, and the hypotenuse is the square root of 2. Uh, in the following table in a second, we're actually going to use that to get some exact values. But as you can see, like for 45 degrees, you have the exact values for adjacent, opposite, and hypotenuse, and so you can get exact values for cosine, sine, and tan of 45. The second special triangle came from taking an equilateral triangle with side lengths of 2 and cutting it in half. When you cut it in half, it makes that bottom side 1, and what it forms is, because the original guy was a equilateral and all the angles were 60, it forms a 30, 60, 90-degree triangle with a hypotenuse of 2, a smaller leg of 1, and using Pythagorean theorem, 2 squared minus 1 squared is 3. The final side here was 3. So these are the two special triangles, a 45, 45, 90 triangle and a 30, 60, 90 triangle. And in your grade 11 course, you use these to get exact values for all these trig ratios, 30, 45, and 60. So I'm going to just squeeze these in here as a visual. 45, 1, 1, root 2, 1, 2, root 3, 60, 30. You guys have them on your notes, so you don't need to write them small there. All right, so just to summarize, we already did 0 and 90, but just to summarize and just to get these down, we're going to look at the exact ratios for all 6 of our trig ratios because we can get them exactly. So for 0 degrees, which corresponds to 0 radians, again, guys, today we're just doing a lot of review, tying in some radian measure. The cosine of 0 is 1. We've seen that. Sine of 0 is 0. The tan is 0. And then for secant, cosecant, and cotangent, we're just taking the reciprocals of those numbers. 1 over 1 is 1. 1 over 0 is undefined. So I'm just going to put, just for short, I'm just going to put UND just to save some room in my table. So cosecant and cotangent of 0 undefined. For 30 degrees, okay, so look at your triangle. So for a 30, 60, 90 triangle, the cosine of 30 is adjacent root 3 over 2, the hypotenuse. So the cosine of 30 is exactly root 3 over 2. Of course, 30 degrees in radians, it's 1/6 of 180. It's pi over 6 radians. The sine of 30 is opposite 1 over hypotenuse 2. It's just 1 over 2. And the tan of 30, opposite over adjacent, 1 over root 3. And the reciprocal ratios are just the flips of these guys. So we have for secant theta would be 2 over root 3. For cosecant theta, just be 2. The reciprocal of 1/2 is 2 over 1. And then for cotangent, it's just root 3. All right, moving forward for 45 degrees. So the cosine of 45 degrees, you can see, is adjacent 1 over hypotenuse root 2. And so is the sine, 1 over root 2. 45 degrees is 1/4 of 180. It's pi by 4 radians. And as we just talked about, the sine and cosine, 1 over root 2. The tangent is opposite 1 over adjacent 1, so 1. And then secant, cosecant, cotangent are just the reciprocals of these guys. Root 2, and the reciprocal of 1 is 1. Let's look at 60 degrees. For 60 degrees, the adjacent and opposite switch. So the cosine of 60 degrees is 1 over 2. The sine of 60 degrees is root 3 over 2. Let's get that down. Of course, 60 degrees is 1/3 of 180, pi over 3. And as we just talked about, the cosine and sine flip because the opposite and adjacent flip. And this time, for 60 degrees, the opposite is our root 3 and the adjacent is 1. Root 3 over 1 is just root 3. And then we get our reciprocal ratios by just finding the reciprocal. 2 over root 3, and 1 over root 3. Lastly, for 90 degrees, which is pi over 2 radians, the corresponding point in the unit circle is 0, 1. So cosine sine 0, 1. Tangent, 1 divided by 0, you can't do, undefined. And the reciprocal of these guys, the reciprocal of 0, undefined. The reciprocal of 1 is 1. And this is interesting. So cotangent is x over y. It's the reciprocal of tan, but you might be thinking, well, how can you do the reciprocal of an undefined number? Look at the definition here. It's just x over y, 0 over 1. The cotangent of 90 degrees is just 0. Now, these ratios can be summarized. At least the cosine and sine, the part that corresponds to the unit circle, can be summarized by a diagram like this, an actual unit circle diagram. And you'll notice on this one, instead of 30, 45, and 60, we've used pi over 6, pi over 4, pi over 3. And we've shown the x, the corresponding point on the unit circle, corresponding to the sine and the cosine, the cosine and sine of each. But we have a little bit of a talking point to discuss. So there is a bit of a difference. If you look at, say, pi over 4, for example, look at what they have here. Root 2 over 2, root 2 over 2. We have 1 over root 2, 1 over root 2. So we're going to have to talk about that. And let's do it right now. So in your grade 11 course, and for most of you guys, you probably just used 1 over root 2 in this situation. But sometimes when we have a ratio and the denominator is a radical number or it's irrational, we like to write it in a different form with a rational denominator. And I'm going to show you guys a couple examples of that. So 1 over root 2, I'm just going to switch to a different color. So I can write that a different way by rationalizing the denominator. I'm going to multiply it by root 2 over root 2. So that's not going to change. It's going to give me an equivalent expression. But look what happens. On top, you get root 2. On the bottom, well, guys, the root of 2 times the root of 2 is, by its very definition, it's just equal to 2, right? Or you can think of it as the root of 4, which is just 2. So 1 over root 2 is actually the same as root 2 over 2. So I'm just actually going to go back in my table. And where I have 1 over root 2, and you guys can add this in a different color or just put some brackets or something. But we can also, I'm also just going to put root 2 over 2. Root 2 over 2. And then and then you can see, and if you Google unit circle, just kind of get a nice visual of what the cosine and sine are for these angles, you're going to see root 2 over 2 most of the time. I don't even know if you'll see 1 over root 2. So you have to keep that in mind, that if you look up a solution and says, hey, root 2 over root 2, I've never seen that before, it's different than 1 over root 2, I'm wrong. Well, no, it's just a different way of writing 1 over root 2, but with the bottom as a whole number. And that can often be helpful. So as we move forward, I might start transitioning from that grade 11 way of writing 1 over root 2 to this updated root 2 over 2, which is equivalent, but it just has a bottom that's a whole number, which will be nice in case we have to, say, add and subtract those kind of numbers. There is another situation here. There's actually two more in our table here. You can see we have 1 over root 3, and we have 2 over root 3. So I'm going to take a moment and just on the next slide show what they're equal to, and then we'll kind of consider the matter kind of closed. So what does, just for consistency, I'll get my blue pen out here again. If we look at 1 over root 3, and we do the same idea and multiply by root 3 over root 3, we get root 3 on top, and the root of 3 times the root of 3 is just 3. And if you look at 2 over root 3, and you do the same thing, rationalize, multiply by root 3 over root 3, you get 2 root 3 over 3. And I'm going to put those in my table too. So I'm going to head back. I would suggest doing it as well, so you have a little resource to come back and look at. So 1 over root 3 is the same as root 3 over 3. That also appears down here, root 3 over 3. 2 over root 3, we showed that's equal to 2 root 3 over 3. and that shows up down here, 2 root 3 over 3. That covers all of our bases. Every other ratio there has a denominator that's a whole number. 6, 4, 3. If it's a whole number, it's like 2 is like 2 over 1. So everything else is okay. So just keep that in mind, guys, as you're moving forward throughout our course and looking at resources online. You're going to see these alternate versions show up. Okay. So, so far, guys, aside from just maybe tying in a bit of radians and writing some degrees in terms of radians, everything we've done here has been review. Maybe showing you guys these alternate forms of 1 over root 2, 1 over root 3, and 2 over root 3 may have been new to you, but arguably that's just a little bit of algebra. No crazy new trig concepts. So for the rest of the lesson here, we're going to do some more review, some types of questions you did in grade 11, but we're just going to kind of tie in radian measure. Okay, so let's continue. Now that we're working with a different way of measuring angles, radians, we have to be careful with our calculators. So, in grade 10, it was just always degrees, degrees, degrees. Grade 11, degrees, degrees, degrees. But now sometimes we're going to be working in radian measure. And so you guys have to be comfortable on your calculators, switching back and forth between degree mode when you need it and radians mode when you need it. When you have an expression and it's like sine 37 degrees, it's kind of obvious that you want to be working in degrees. If you see an expression like sine 2.17, that's obvious that that's in radians. Remember, when it's radians, we just write the number. It's assumed to be radians. We want to be in radians mode. So this exercise, all you guys are doing here is we just want to get you guys comfortable using your calculators, switching back and forth. So I'm just going to pause here, and I'd like you guys to try A, B, C, D, E, F, switch to radians mode for D, E, F, give it a try, and then unpause when you're ready, and I'll see you in a moment. All right, guys, then we're back. And so for A, B, and C, you had your calculator in degree mode, then hopefully you figured out how to put yours into radians mode. And you just got to be careful now, because sometimes we want degrees and sometimes we want radians, and you don't want to be working in degrees doing a radians problem. It's a classic kind of mishap that happens in the classroom. A student will, maybe it's happened to you in grade 10 or 11, where a student writes a whole test with their calculator in radians mode when they should have been working in degrees, or vice versa. For me, I don't know if you can see, for me on my calculator, I have a setup right in the middle there, a setup button. So I press my setup button. It's hard to do this. I go to setup and I can change to degrees and radians from there. You got to have your own calculator and know how to use it. If you want some coaching on that, feel free to reach out. My plan is to do GH and I with you guys. So how do we evaluate reciprocal ratios? You guys did do this in your grade 10 course. What we do is we make use of the fact that cosecant in this case is the reciprocal of the sine function. Cosecant 107 is the same as the sine of 107 degrees. So you can evaluate sine 107 and then divide by 1, or you can just do that in one step. And I need to take my own advice and switch back to degree mode. Just got caught there. So 1 divided by the sine of 107. So I can see this is just what I'm typing in. 1 divided by sine 107. So none of what we're doing is designed to be crazy complicated. It's just right now I'm trying to make sure that we're all very comfortable flipping back and forth and knowing the ins and outs of our calculators. Secant 190, what is that? It's the reciprocal of cosine. So you can do cosine 190, write down the decimal, then divide, or you can just do it all in one step. Get negative 1.0154. Now I can see that I is working in radians, so I'm going to switch my calculator to radians mode, and then I can try I. We know that cotangent 4.54 is equal to the reciprocal of the tangent of 4.54 radians. 4.54, and I got about 0.1741. Okay, just getting comfortable evaluating reciprocal ratios, switching back and forth between degrees and radians. All right, let's continue. I think I've got 3 more. Oh yeah, one thing to note, another way to do this, like for cosecant 107, what you could do is punch in sine 107, and then some of you guys may have an actual reciprocal button on your calculator, which will do the 1 divided by for you. That's just another option as well. Okay, so let's do a few where we just get used to, because a lot of times when we're working with radians, a lot of times we write these in terms of multiples of pi. And right now, we're not worried about getting exact ratios right now. Right now, I'm just worried about, can you actually put this into your calculator and get the correct ratio as a decimal? I'm not worried about exact ratios right now. So sine 7 pi over 6, we're obviously working in radians right now. And we literally just punch that in and use your pi button. So for example, here's what I have. You can see it gives you exactly negative 0.5, but you can see how I punched it in. Just literally punch it in as you see it. Use your pi button. So that's negative 0.5. What we don't want to do is, okay, convert this radians into degrees and then find the sine of however many degrees this is. For example, I'll do it just for this one. So 7 pi over 6 radians equals, to get that in degrees, we would take 7 pi over 6 and multiply by our conversion factor, which is 180 divided by pi. Pi is divided out. 180 over 6 is 30, and you're left with 210. So if you guys do the sine of 210 degrees, it's also negative 0.5, but we would like to get comfortable just being able to work in radians on our calculator. So you can try these last two on your own. I'll just do them along with you guys here. So cosine 7 pi over 4, literally just punching it in as I see it, making use of my pi button. We just want to get comfortable doing this. Nothing fancy here, 0.7071. And lastly, cosecant of 5 pi over 3. Remember, for evaluating these reciprocal ratios, just do 1 divided by, and I'll show you guys how I punch this in. This can all be evaluated at once. 1 divided by the sine of 5 pi over 3 gives you about negative 1.15. I said 4 decimal places. Okay. So again, nothing there, nothing crazy new, no new concepts there. We just took some time, and hopefully you've now built up a bit of a comfort level with your calculator and being able to work in radians, switch back and forth between radians and degrees, and calculate ratios. When you need a decimal for like an application, you can do it quickly and efficiently and accurately, hopefully. All right, so we've got used to our calculator, switching back and forth between radians. Let's do a few questions you guys might have seen in your grade 11 course. Again, we are reviewing and then just tying in some radian measure. A lot of review today. So earlier, we found the exact ratios for, well, we have 0, 90, 180, 270, but we could get some angles in between, 30, 45 degrees, and 60, or pi by 6 radians, pi by 4 radians, pi by 3 radians. But it turns out you can find exact ratios, not just for those guys, but for any angle that's related to those guys. And you can do it using the cast rule. So let's review how to do that. Doing that requires something called the reference angle. The reference angle is the angle a terminal arm makes with the x-axis. So I wanted to just do a couple quick ones with you guys. You would have done this in your grade 11 course, so this is purely review. So what I might do with my class who's learning this right now, might say, okay, just draw the 0, 90, 180. And if you're drawing 165 degrees, just do a rough sketch of where that would be. It'd be around here, right? This is about 165 degrees. The reference angle is the angle that this angle makes with the x-axis. The reference angle here would be 15 degrees, 180 minus 165. So we call this the reference angle. It's always acute. And what you guys saw in grade 11 is that the trig ratios for these reference angles are the same as the trig ratios for the original, just the signs are determined by the cast rule. For example, if you do cosine 15, and I'm going to make sure I'm in degree mode here. If I do cosine 15, negative 0.9659, blah, blah, blah. If I do the cosine of 165, you will notice it's the exact same number, but negative. Negative because we're in the sine quadrant where cosine is negative. So let's do a couple more, and we're just going to find the reference angles. So if you want to pause the video and give those a try, that would be really great. If you want to follow along with me, that's great too. So 250 is somewhere in here in our third quadrant, maybe a bit closer to 270. So all the way around here is 250 degrees. So what does that make our reference angle? Well, the negative x-axis is 180. That whole angle is 215 degrees. It's 70 degrees more. This is the reference angle, 70 degrees. We need to be comfortable calculating these acute reference angles, always with the x-axis, always, always, always. All right, now we're going to do the same thing, but working with radians, okay? So it might be helpful for the first one to, let's label those special angles we know. 0 radians, 90 is pi by 2, 180 is pi, 270 is 3 pi by 2, and of course 2 pi radians would be 1 full revolution. 7 pi over 4 is between 3 pi over 2 and 2 pi. It's somewhere in here, and if you're a little unsure where that is, that's okay. And what's the reference angle? Well, the reference angle, and again, this is our angle here is 7 pi by 4. What's our reference angle? I might go to green just to do this calculation here. Well, basically it's, well, what's the difference between 2 pi and 7 pi over 4? How much is left? So to get the reference angle, we're going to do 2 pi minus 7 pi by 4, which is equal to 8 pi over 4 minus 7 pi over 4. The reference angle here in radians is pi over 4 radians. Alternatively, and this is the long way, we ideally don't want to do this way though. 7 pi over 4 is 315 degrees. You can get the reference angle in degrees, 45, and convert it back, but we would like to be able to work with radians. Let's try D. In your grade 11 course, you learned you can have negative angles in standard position. What that just means is we go back the other way. So 0, negative pi by 2, negative pi. And negative 4 pi over 3 is a little bit more than negative pi. Goes around like this. Theta equals negative 4 pi by 3. And so let's calculate this reference angle. Again, it is possible just to convert to degrees, figure it out in degrees, and then go back. But let's just calculate this. So we've gone from 0 back to negative pi and a bit more. So we've rotated 4 pi over 3 radians in the clockwise direction. How much more is 4 pi over 3 than pi? You can just subtract them. 4 pi over 3 minus pi. That's 4 pi over 3 minus 3 pi over 3. It's equal to pi over 3. So my diagram is not quite to scale actually, because pi over 3 is 60 degrees, but that's okay. So we have to be comfortable calculating reference angles. There's really just no avoiding it. We've done a few examples now in our notes, and we're going to use these reference angles to find exact trig ratios for all other angles that are related to 30, 45, and 60, or pi by 6, pi by 4, and pi by 3. Let's continue. So I'm going to do a few of these guys, and then I think I have a nice big summary of the unit circle and kind of all the exact ratios that could be possible. But we'll get there in a second. Let's do a few by hand. So starting off easy, actually. Um, Theta equals 2 pi. Well, what angle is that? Let's draw it. 2 pi radians, we know actually is one complete revolution, right? One complete revolution. That's theta equals 2 pi. You know that, on the unit circle, you'd be finishing off, it's the 0.10. So there's not a lot of work here. This we can just get by the fact we know 10 is the point on the unit circle. So the cosine would be 1, the sine would be 0, the tangent would be sine over cosine, 0 over 1, which is 0. And then our other guys are just the reciprocals. I just realized I have cosine here and cosecant here. Didn't mean to psych you guys out. The reciprocal of sine, undefined. The reciprocal of secant is the secant is just the reciprocal of cosine. 1 over 1 is 1. And the reciprocal of 0, so cotangent, is undefined. And if we go back all the way to our table here, it's the exact same values that we got for 0 degrees, because 0 and 2 pi are the same angle. They share the same terminal arm. Okay, let's try another one, not so obvious here. Okay, so 3 pi over 2. Let's draw this out. So 0, pi over 2, pi, 3 pi over 2. Oh, this is just equivalent to 270 degrees. It corresponds to this point on the unit circle, which would be 0, -1. So another one that's not so bad. Cosine is 0, sine is -1, tangent is sine over cosine, which is undefined here. And then for cosecant, reciprocal of sine, -1. Secant is the reciprocal of cosine, 1 over 0 is undefined. And our tangent is undefined. Or our tangent is y over x, -1 over 0. Cotangent is x over y, 0 over -1 actually gives you something meaningful, 0. So these guys, just draw the angle and use the fact that these are nice points on the unit circle. In our case here, 1, 0, and 0, -1. But what if it's not? So how about 7 pi by 4? So we actually did a bit of the legwork for these earlier, if you recall. I'm going to switch to dark blue, actually. Having a hard time finding my cursor. 7 pi over 4, we drew this one, right? And we already found the reference angle. This is 7 pi by 4. And the reference angle, pi by 4 as well. In your grade 11 math course, you would have talked about different ways of doing this kind of problem. So there's many ways to approach it. My personal choice is to use the cast rule and use what you already know about the exact ratios for pi over 4. So I'm going to write down the cast rule here, CAST. So right away, we know that the sine will be negative, the tan will be negative, right? Because we're in the cosine quadrant. The reciprocals of those, cosecant and cotangent, will be negative as well. So just pop in the negatives. And now the ratios, because the pi over 4 is related to 7 pi over 4, we can just use the ratios for pi over 4. We already did them all, right? We already summarized those in our table. They're right there. 1 over root 2, or root 2 over 2, root 2 over 2, 1. We just got to copy them out. So I personally don't mind these kind of questions. And this is the strategy I use. Draw the angle, find the reference angle. From there, apply the cast rule, which are positive, which are negative. And from there, just fill in the gaps. So the cosine of pi over 4, I'm going to use our new version, root 2 over 2. Sine pi over 4, root 2 over 2. But we got the negative in there already. Tangent of pi over 4 is 1, but this time will be -1. And now we just take the reciprocal of these guys. What's the reciprocal of the reciprocal of negative root 2 over 2. It would be negative 2 over root 2. The reciprocal of our cosine would be 2 over root 2. And the reciprocal of negative 1, negative 1. Now, for these reciprocal ratios, um, uh, these are okay as they are. But I might just maybe up here, just show that 2 over root 2, we can rationalize that. If you multiply by root 2 over root 2, see what happens. You get 2 root 2 on top. Root 2 times root 2 is actually 2. And you can see that 2 divided by root 2 is actually just equal to root 2. So if you were doing this problem, I'd mark 2 over root 2, right? But it's actually just equal to root 2. And if you're looking up answers in a solutions manual, for example, you would probably see it simplified as root 2. Okay, let's do one more. Let's apply our strategy. So let's just draw this one back out again. So we did this earlier. So negative 4 pi by 3 got us up to around here. And we had a reference angle of pi over 3. Can you guys take a moment, maybe pause the video, use the cast rule? Which quadrant are we in? Pop in the negatives for their trig ratios. They're going to be negative. C, A, S, T. And then look up the exact values for pi over 3. And then we just got to pop them in. We can all do this. All right, so I'm going to continue. Hopefully you tried it, maybe gave the video a pause, but we're in the sine quadrant. Only sine is positive. So cosine will be negative, tan will be negative, and the reciprocals, secant and cotangent, all going to be negative. As far as the what the values are, let's go back and look at the exact values for pi over 3. And you guys have all your notes all the time, right? There's no reason you just can't have these values out. Cosine of pi by 3, a half. Sine pi by 3, root 3 over 2. Tan of pi by 3 is root 3. That's just staring us in the face, right? So let's just get these in. Let's pop them in. Cosine 1 over 2. I'm just double checking that. Yeah, 1 over 2, root 3 over 2. 3 over 2. Tan was root negative, it would be root 3, but negative root 3 because we took care of the signs ahead of time. And now just do the reciprocals. 2 over root 3. For secant, it'll just be negative 2. And for cotangent, the reciprocal of root 3, 1 over root 3. But of course, it's negative. Now keep in mind, probably not going to see 2 over root 3 in any solutions manual or textbook. They're probably going to rationalize that and write that as 2 root 3 over 3, like we talked about earlier. Same with 1 over root 3. You're going to see that as negative root 3 over 3. All right. So arguably, guys, everything so far, again, we've done a lot this lesson, but I've tried to do a very deep dive into reviewing some grade 11 stuff. That's why we're taking a bit longer. It's going to happen once in a while. A very nice tool just to have, maybe print off, find one you like online, is something like this, where it shows you all of their critical angles, 0, 90, 180, 270, as well as what they are in radians, 0, pi by 2, pi, and 3 pi by 2. And it shows 30, 45, 60, but then all of the angles that are related to those guys. And this particular one has all the angles in radians too. And what this has is it has the cosine and sine for each one of these guys, right? So for example, for this one, now I don't have this on your lesson sheet, but if you just Google the unit circle, you're going to get something like this coming up, and it'd be very worth your while to either like make your own or print one of these off. But just to quickly show how we could do a problem using one of these, let me take one we haven't done. Let's take 7 pi by 6. What if I was looking for, I don't know, the cotangent of 7 pi by 6? Well, I have the corresponding point on the unit circle, x, which is the cosine of that angle, and y, which is the sine of that angle. And remember, cotangent is equal to x over y, right? Cotangent of an angle, x over y, where x and y are the coordinates in the unit circle. And so for here, we can do, okay, so the cotangent would be the x value of so it'd be minus root 3 over 2, and then divided by negative 1 over 2. And then we can just work this out. That's negative root 3 over 2, dividing by negative 1 over 2. That's like multiplying by negative 2. The negatives cancel out, the 2's cancel out, and you're just left with root 3. The cotangent of 7 pi over 6 is root 3. So this unit circle, not only does it show you the cosine and sine of all these angles, it can help you do a multitude of problems, like finding the exact value for cotangent of 7 pi over 6 or something like that. So my suggestion, Google it, find one you like, copy it out, print it off, and just keep it with you and just have it as a resource. Very, very, very helpful little aid. Okay, let's continue, guys. So we're going to do a little bit more with exact ratios. So we're going to determine an exact value for this, the cotangent of 5 pi over 4 plus the tangent of 11 pi over 6 times the tangent of 5 pi over 3. And I'm going to make use of my unit circle. There we go. So our first one is cotangent 5 pi over 4. So I'm going to find 5 pi over 4 on my unit circle. 5 pi over 4 down here, 225 degrees. The x is negative 2 over root 2. The y is also negative root 2 over 2. And I can see that x over y there, and I'll write it out. Negative root 2 over 2 all over negative root 2 over 2. That just equals to 1. So the unit circle coming in handy, saving the day here. What's my next one? So cosine of 5 pi over 4, that's 1. All right, the tangent of 11 pi over 6. All right, 11 pi over 6, that corresponds to 330. And we got root 3 over 2, negative 1 over 2. And we're trying to do the tangent of that. 11 pi by 6. So tangent is, in terms of the unit circle, y over x. And for this point, the y is negative 1 over 2 all over. The x is root 3 over 2. That's like negative 1 over 2 times 2 over root 3. And we get negative 1 over root 3. Now, I'm going to rewrite that using our other form. That's the same as negative root 3 over 3. Pop that in. Plus negative root 3 over 3. And then finally, the tangent of 5 pi over 3. Let's find that. 5 pi over 3. I'm getting old. I'm almost 40, and I literally can't find 5 pi over 3. Where is it? Okay, it's 300 degrees. There we go. The x and the y. So the tangent of this one, I'll squeeze this work in here. Tangent of 5 pi over 3. It's y over x. So it's negative root 3 over 2 divided by 1 over 2. That's negative root 3 over 2 times 2 over 1. This works out nicely just to negative root 3. So now that we found those exact values using our unit circle, we can just clean this up. So negative root 3 times negative root 3 is actually just positive 3. 3 divided by 3 is 1. And that crazy expression just equals to 2. And we can get that pretty quickly and efficiently by using the unit circle. And remember, this table will help you out too. You guys learned in grade 9. Remember, on the unit circle, cosine is the x coordinate, right? Cosine is the x coordinate. Sine is the y coordinate. the tangent is ratio of y over x. Secant is just the reciprocal of x. Cosecant is just the reciprocal of y. Cotangent is the reciprocal of tan x over y. If you guys have the unit circle, you can make use of this resource. Look up the angle, look at the point, x, y, use the appropriate combination. And I really suggest you guys copy this unit circle down or print off a copy that you can use. All right, guys, been doing great. We're going to do one last thing. We're actually just going to solve a trig problem, and we're going to have an exact answer for this one. So Ravinder flying a kite, and the kite has a 50-meter string, and the sun is directly overhead, making a shadow. And so initially, the string makes an angle of pi by 6 radians with the ground. So if you're just doing the mental conversion, that's 30 degrees. When the wind increases, the angle goes higher. So the kite will fly higher. The angle changes to pi over 3 or 60 degrees. And we're going to find an exact expression for how far the shadow moves. So this might have been a problem that you could have got in your grade 10 course just with SOHCAHTOA, but just in our course, we're just going to tie in some radians and leave our answer as exact. And then in part B, we'll find the answer approximately. So what you guys should do, maybe pause the video, try making the diagram on your own. Then I'm going to put a diagram up on the board here in just a moment. So I'll assume you've tried drawing that one if you wanted to. And yeah, let's get a diagram up here. Where's my cursor? There we go. All right, so I'm going to draw it in the top left here. So what we had, I'm just going to kind of think of things in terms of the first quadrant in our Cartesian plane. So initially, our kite was at an angle of pi over 6 radians, so like 30 degrees. And the string length was 50 meters. And the shadow would have been, if we start at the origin, then this point here, I'm going to call this x1. Then the shadow is x1 meters long. And I might just actually find that right now. So how can we get that? Well, we're looking for this bottom side. It's adjacent to pi by 6. So we're doing the cosine of pi by 6 equals opposite, calling that x1, over hypotenuse, which is 50. But now, instead of just using our calculator to get a decimal value, we actually know what the cosine of pi by 6 is. Let's go to our unit circle. Pi by 6. Cosine corresponds to the x value, root 3 over 2. It's right there for us. Unit circle is awesome. Root 3 over 2 equals x1 over 50. And we can just clean that up. X1 is equal to 50 times root 3 over 2. 50 over 2 is just 25. 25 root 3 meters was the length of the kite shadow initially. And then, I haven't used purple in a while, the wind picks up, and now our kite is at a different angle. The kite string is still 50 meters long, but now we're at an angle of pi by 3, or 60 degrees, and now the shadow is shorter. How much shorter? That's what we're trying to find. Well, let's find the length of that shadow. And we can do it in a similar manner. This time, we're finding the adjacent side still, cosine pi over 3. We're calling this guy x2 over hypotenuse 50. And we know the exact value for cosine pi over 3. You do not need to have these memorized. Go look at your unit circle. Pi by 3, cosine, it's the x value. It's 1/2, right there, 1/2. Y flip all the way to the end, we got 1/2 equals x2 over 50. And you can get this by multiplying up to 50. You probably get this with mental math, but it's 50 divided by 2, 25 meters. And so for A, for the exact distance they're apart, x2 minus x1, that should be the opposite way around, the bigger one minus the smaller one. x1 minus x2. So we had x1 was 25 root 3, and x2 was 25. Now, this is exact. Sometimes it's useful in a situation like this. You can actually factor that to 25 times the root of 3 minus 1. Personally, the first one would be fine for me, but factoring is always a good idea if it can make things simpler. So that's it. We've answered the question. The kite shadow has moved 25 times root 3 minus 1 meters. Now, how much is that to the nearest tenth of the meter? It'd be pretty silly if you know I asked my wife, or if my wife asked me, hey Andrew, like how far do you want me to move this couch or something, and I said, hey honey, maybe we move it 25 times root 3 minus 1 meters. Like, that's obviously very silly. So let's find this out. So the root of 3, I'll just keep a bit of accuracy. Root 3 is about 1.732. Now you guys could just crank all that into your calculator at once if you wanted to. It's like 25 times 0.732 times 25, 18.3 meters. So the shadow moved about 18.3 meters. All right. We did it, guys. So a little bit of a beefier lesson for sure. But I wanted to do a lot of grade 11 review because it's going to set it up it's going to set us up well for the rest of this unit and the next unit. Guys, I can't stress enough how helpful getting your own unit circle is going to be. You can see that we can find exact values for cosine, sine, all kinds of angles just by looking up. For cosine, look at the x value. For sine, look at the y value. For tangent or cotangent or secant or cosecant, just do the appropriate 1 over x, 1 over y, x over y, or y over x. This unit circle is going to help you a ton. So yeah, and you know what? I will once I post this lesson, I'll find one. I'll actually find this exact one and just post it under this lesson. All right, so good job, guys. We reviewed a ton of grade 11 stuff and made some connections with radians. In our next lesson, we're going to start looking at equivalent trigonometric expressions. Well, that's kind of a fancy way of saying identities. So hopefully you're not having some PTSD from your grade 11 course when you did trig identities, but it is where we're going for the last kind of phase of this unit on trigonometry. I suggested some practice to you guys there. A lot of that practice is just evaluating ratios and just making sure you're comfortable going from degrees to radians and modes on your calculator, evaluating, getting accurate ratios when you need them, and doing some exact some calculations of some exact values. Now, I showed you guys the grade 11 way using related angles, and then we move to just using the unit circle. And I'm okay if you just start practicing getting comfortable using your unit circle. Okay, so great job today, guys. Hope you guys are doing well. Take care, and we'll see you soon.